And as a second problem, second topic, let's consider a shaft design problem. Okay, so this is also have analogy with axial loading chapter. In axial loading chapter, we considered like a reliable and safe design, where the maximum stress in the structure is smaller than the allowable stress, and if the allowable stress is larger than the maximum stress of the structure, then we can say that is reliable design. Okay, so we can do similar design example for torsional loading. In the example we're going to adapt is engine and power transmission system in a car. Okay, of course this is a super simplified view, and in realistic engineering practice, yeah, you have to consider much more complex stuff, but you are just a beginning mechanical engineer, so yeah, let's be satisfied with the simple example. So here we're gonna consider engine. Yeah, of course we might not have engines in 5 or 10 years, because most cars may be replaced with electric car which utilize motors, but still we have many gasoline cars. So let's use this example with engine. So this engine somehow is rotating with constant angular velocity w. Okay, yeah, so this is a constraint to make the problem simpler. Yeah, if the angular velocity is not constant, you have to consider like acceleration of this engine, and it will give additional complexity to the problem. Okay, so by limiting the problem with constant angular velocity, you can say that because angular velocity is not increasing or decreasing, mechanical equilibrium, the force or torque summed up to be zero, and by making that mechanical equilibrium assumption, you can make the problem mathematically simpler. Okay, so that's the idea behind the constant angular velocity here. And with this constant angular velocity omega, yeah, engine is exerting te, torque exerted by engine to the transmission system, and the shaft has the diameter of d1, and there is a gear, and gear has diameter of large d1, and it's connecting to another gear with like a large d2, and this system has shaft of diameter d2, and it's transmitting powers to the other parts of the car. So the problem is asking when engine rotate with constant angular velocity w, what power p prime and torque t prime acts on the other parts of the car. Yeah, so yeah, we want to obtain. Okay, so the engine is exerting torque te, then there is gear with different diameter, and how much torque will be exerted on the other parts of the car through the transmission system. Okay, that's the first question. And of course, in addition to torque, what will be the power? Yeah, power exerted by engine is torque multiplied by angular velocity w, so which we have already learned in freshman physics. Then what about power delivered to other parts of the engine? Of course, in realistic problem, there is like a heating problem, there is a noise problem, which dissipates energy and wasted energy. But here we're not gonna consider any noise, we're not gonna consider any heat transmission problem. Okay, we just simply consider mechanical energy transfer, and that's it. Okay, and in addition to that, second question is, given allowable stress tau allowable, tau ALL, what will be the minimum and d1 and minimum d2? Okay, the shaft must be thicker than minimum d1 and minimum d2. If shaft is too thin, yeah, you might expect like a fracture under the torsion. Okay, so we have to approach q1 and q2 based on the knowledge we have learned until now in ME231, and of course we have to borrow some knowledge from freshman physics. So let's first consider first question. What will be the power and torque delivered to other parts of the system, which is here. Yeah, so as I told you, we are not considering any like a noise and heating problem, so that there is no energy dissipation. Then what you can expect is energy conservation. Okay, so from energy conservation, the power given from engine must be delivered 100% to the other parts of the car. So P and P prime must be equal to each other. And P is T multiplied by angular velocity W, and that's the answer. Okay, so answer for P prime. What will be the torque T tau T prime? Yeah, that gives us a little bit of more fun. Okay, so let's consider like a side view of this section. Okay, so we have two gears with D1 and D2 diameter. So if I draw it, it looks like this. So let's imagine that the smaller one, D1, is rotating with W, and because this guy is rotating in counterclockwise, it'll make the second gear to rotate in clockwise, right? So it'll rotate in clockwise, and to make clockwise rotation, the between this the touching zone between these two gears, the force must act on upper direction. Okay, and there is of course Newton's action and reaction principle. So the force exerted on the right the larger gear must will exert like a reaction force to the left gear one in opposite direction with same magnitude. So you can have force diagram in this way, and because of this force, it will exert the torque on the gear. Okay, so if we look at this as a whole, it's a little bit confusing. So let's try to do divide and conquer straight ahead. So we're gonna consider this small section of the gear. So with D1, so here we have engine, and engine is exerting TE torque to the one part of the shaft. Okay, as a reaction, this part of the engine will have force in this direction, and that force exert opposite direction torque to the shaft. Okay, and because as I told you, we are having constant angular velocity omega condition to make and to keep the angular velocity constant, the torque summed up to be must be 0. Okay, so TE minus torque exerted by this force F times radius, which is D1 over 2, must be 0, and we can obtain that F must be 2 times T over D1. Okay, and if I draw this using double arrow notation, it looks like this. So this is the free body diagram of the first shaft and first gear, and this is the force we obtained from the first problem. Now let's move on to the second problem. So the gear is having force in that direction, so we are now considering this guy. Okay, and due to this force, what you can expect, there is a torque F times radius, which is D2 over 2. And of course, if the angular velocity of this guy is constant, angular velocity of this guy is also constant, which means that to deliver the power to the other part of the system, and as a reaction, the other part of the car will have torque to the shaft. There is always action and reaction principle, and let's say that this torque is T0. Okay, then T0 minus F D2 over 2 must be 0 to make the angular velocity of the shaft to be constant. Okay, then we obtain that the torque that is exerted to the other parts of the car here must be same as F times D2 over 2. And if we plug in the value for F, because F is not provided in the problem, the problem only provided us TE, then we end up having T0 exerted on the other parts of the car turns out to be D2 over D1 TE. Okay, so what's the implication here? So of course, if I draw the free body diagram and double arrow notation, it looks like this. Anyway, the implication of this equation is that by tuning the ratio between D1 gear and D2 gear, you can change the torque exerted on the other part of the system. Okay, so of course, by changing the ratio between two gear size, you're gonna have different angular velocity ratio. But if you somehow choose like a slow angular velocity but with a larger torque, you can have larger ratio. If you want to have like a faster angular velocity with smaller power, you can have like a smaller ratio between d1 and d2. Okay, that's what you are doing with changing the gears in your car, like a gear 1, gear 2, gear 3, gear 4. There is always compensation. We can have either higher angular velocity or as a sacrifice of the torque, or we can have higher torque but with slower angular velocity delivered to the other part of the system. Okay, so this is a simple example of power transmission system. Okay, so after talking about this simple like power and torque transmission, let's move on to second question. The second question is structural mechanics question. So what will be the minimum d1 and d2 from given allowable stress? Suppose that the material scientist who is making the shaft provided us the allowable stress for this shaft, and we want to make a the diameter of the shaft larger than some critical value, such that under torque the shaft does not fail. Okay, so how can we handle it? So the what you have to consider in torsion loading problem is in contrary to axial loading, where we had like a constant and uniform normal stress over the entire cross section, we have different shear stress on different parts of the cross section. We're gonna have higher shear stress as we have further distance from the center. Okay, so this maximum stress must be smaller than allowable stress, and if we obtain the expression for maximum stress, it can be written as C1 times T divided by J1, and C1 is the radius, and radius is D1 over 2. This is the radius of first shaft, and this is the torque exerted by engine, and J1 we can obtain from the previous lecture, which give us pi over 2 C1 fourth power. Okay, and C1 is D1 over 2, so we can obtain the expression for J1. Now after plugging in all those expressions, we end up having this is tau max, and tau max must be smaller than tau allowable. Okay, then after massaging the equation in terms of d1, and we have this inequality equation, d1 must be larger than or equal to this expression, like 16 times t over pi tau allowable to the 1/3 power. Okay, so this is the expression regarding t1. What about d1? What about d2? The only difference between d1 and d2 is we are using same material which has same allowable stress, but we have different torque T0. Okay, so to solve the minimum diameter criteria for shaft 2, instead of TE we have to use T0. Okay, instead of T prime we have to use T0, and T0 turns out to be D2 over D1 TE, and that's the answer for D2. Okay, so if you want to exert higher torque, our equation says that we have to use like a thicker shaft, which is consistent with our intuition, right? So with that, we just solved like one example problem, in power transmission and torque transmission, plus structural design problem with where we set the allowable stress larger than maximum stress criterion and find the minimum size of the our structure. Okay, so with that, let me finish my video on second topic here, and move on to the next topic in next video.